basically you have done the homework, so probably you guys have done this as well, right? Something similar, right? You can use the Excel file, then you can create the table very easily. And one more thing. I have downloaded this one. 4.5. Okay. Yeah. All right. So, what was the asymptote equipartition property? Basically, we use the convergence in probability, right, to show that this probability right here basically is bounded above and below with roughly the probability is 2 to the power of minus nh. That's it, right? Then how many bits do you need in order to describe sequence of bits of length n, right? That is basically nh bit, right? So if you have n which is, let's say, 100, and then nh is just 10, then instead of you need 100 bits to represent the sequences of length 100, you can use 10 bits to describe, on the order of 10 bits to describe it. So instead of 100 bits, you can represent these sequences with about 10 bits. That's what this theorem is about. The asymptotic equipartition property. And basically, the exact proof was given in Shannon's 1948 paper. Okay, so in today's standard, this is very rough, too much approximation, you may say. Right? As you can see, if you have done the homework, if you create a table, it doesn't fit very well, right, with the reality. But as an argument, or as a, so you may consider this as the original paper, the first paper that was written in 1948, right, where none of the people talk about these things, right. So you can be rough, right. The original paper is not precise, as you would see in recent years, right? When you take a look at the papers in recent years, very, very precise. The proof is beautiful, very, very rigorous, but nothing new. Okay, but if you do something original, then you have a lot of things to prove, right? So things can be rough, right? An approximation, not perfect, right? But if the idea is very good, then it sails through, okay? So that's the difference between the pioneering research versus incremental research. If you do incremental research, you just build on top of what others have done, so you can make precise things, become more beautiful, things fit together very well, right? But you are just adding a single brick in an apartment building, for example, right? So, but this type of rough ideas, right? If you use develop this type of ideas for original paper, right? Then that's good enough. Okay, so you can think of it that way. Okay. All right, and so like I said, this is very rough. So at this point, I can open up the Excel sheet that I have just downloaded, right? This one. So for example, I have chosen p is equal to a small number in order to illustrate the point. Okay, So if I consider length of 100, it's too small, 그지? 작게 할 필요가 없지. 보이죠, 이제? Yeah, so length of 100, right? And then in normal sense, average person would say that I need n bits to require, n bits are required to represent any sequence in this random experiment, right? So this random experiment is IID samples of x1, where x1 is 1 with probability p, 0 with the probability 1 minus p, right? So that is what this one is about. So p is selected to be very small, right? So in such a case, the probability of occurrence of 1, very small, and then in this case, if we run, let's say, 100 of them, IID, what do you think is the expected number of ones in the sequence? 5, right? 5 is the most typical one, right? That you will see, right? That's the average as well. So n times p is basically it, right? So it is 5. And then if p is given, we certainly know how to calculate entropy, h, right? So entropy is a function of p only, right? So we can calculate that one, and then this is the formula, right? Basically, I'm doing p times log 2 over p plus 1 minus p times log 1 minus p, and then take the negative sign for the whole thing, right? Then we get this number right here. But I figured out that Excel doesn't have log 2, so I have used this equality right here. Log 10 divided by log 10 2. Okay. So basically, that's the entropy, and this is the block length or sequence length, and this is the epsilon. In this particular case, I have chosen 10, which is very huge, right? But compared to NH, this is, you can consider it small, right? And then remember the convergence in probability. For each epsilon you choose, you let n goes to infinity, right? So if we let n goes to infinity, you can have this within the bound, okay? That's the claim of this theorem. And probability is upper bounded by this, lower bounded by this, okay? So you can just take a look at the order. 10 to the minus 6, 10 to the minus 12, okay? That's it. And then let's take a look at the result. Basically, m is the number of ones in the sequence of 100 random variables. And as we have expected, 5 is the most typical one, as you can see. So how many such sequences? 100 choose 5 of them, so which is huge number, which is this one in this particular case. And then the probability of population and the probability of each sequence x, right? That is the order of 10 to the minus 9, right? So it's certainly fit within this interval, right? And the population probability is this. So if you choose what is the most typical sequence group, then you can just choose this one. 5 number of ones in the sequence of 100 is the most typical one, right? If I have to include other items closer to this, basically you can choose m is equal to 4, which is this, and 6, which is this, the probability of population. Then basically you can add them up, right, to calculate the size of the population, right? And then if I include, m is equal to 3 and 7, then you may include these and these as well, okay? So this way you can just play with this, and then you can make sure that, the asymptotic equipartition properties kind of works, right? It's not precise, right? But you get the rough idea. That's good enough, okay? So you can play with this. So basically, what this is telling you is that the probability of a sequence of 100 is upper and lower bounded by this number, which is parameterized by n and h, okay? So if p is given, you can calculate h of p, right? And then n is the length of the sequence, okay? So in that particular example here, since nh is 28, then the size of a typical set is like on the order of 10 to the power of 11, right? And so those are the things that you can say, okay? And in this particular case, since nh is 28, right? Instead of 100 bits to represent each sequence, you can represent each sequence in the typical set with the length on the order of 29. So if you have 29 bits, then you can represent each sequence in the typical set. Those sequences not belong to the typical set, they will rarely occur, so you don't pay less attention. Okay? So that's basically the compression theory. Okay? So you can compress 100 bits to 28 bits, right? In this case, we talked about compression of, compression ratio of about almost 70% compression, right? In the case of where p is equal to 0.05, sorry. All right, and this one is basically the theory of AEP, and that one, the proof is given using the convergence in probability, which is a rough idea as well. It's not almost the sure sense convergence. And that is basically what AEP tells us. So for length and IID sequence of random variables, NH bits are good enough, okay, to describe the length of 100 sequence. So the size of the typical set is 2 to the power of NH, and each sequence occurs with the probability of inverse of this probability, which is that, okay? So give a little, take away little, like by epsilon much, right? That's the rough idea. So NH, H is the number smaller than 1, so NH is always smaller than or equal to N, right? So there is a compression effect. And so that's what the AEP is about, right? So since you guys have done the homework, right, this could be understandable, right? Right? Do you have any question on this one? IID case? Now I am trying to move on to chapter 4 material, which is dependent case, not IID case, okay? Any question on this one?
그 typical set과 non-typical set의 구분에 대해 한 번만 좀 정리해 주실 수 있을까요?
Okay, yeah. So typical set, all right? 그러면 I will use this as well, okay, again. So here I could define, upper and lower bounded by this number. The probability should be upper bounded by this much, and then lower bounded by this much, right? For this epsilon. Okay, then I can take a look at the table here. So this one was the probability of a particular vector, right? So I have to look at this column, probability of a vector x of length 100. And then this one says each one occurs with the probability of 10 to the minus 9, minus 8, minus 7. So this line should be somewhere between the set for m is equal to 2 and m is equal to 3. So let's just include this one as well. Okay, so I can have this bold faced. Okay, and then how about upper bound? 10 to the minus 12. Okay, I can maybe include this, maybe up to these 3, right? Like that. Then right here at the center, we have this probability of a population getting smaller, like this. And then if we sum them all up, that's the probability of a typical set. If you run the experiment, X is a random outcome of this experiment, and that belongs to this group with the probability of some of these numbers. Right? So what is that sum of the numbers? So this is like 0.2, 0.2, 0.2, 0.6, right? And then 0.8, 0.9 something. So almost 90%, right? It falls within this bound. So basically we can talk about any one of those x belongs to this group where number of 1 is 2. All right, let me bold-face these as well. So if you run the experiment, this is the size of the whole set, sample space, and then these are the x's. Each one is 100 tuple vector, right? Each one of them. And then this one, we can divide this into sets. How many? So here, this is a set where number of 1 is equal to 0. There is only 1 actually, right? All zero sequence. And then, how about this one? M is equal to 1. There are how many number of vector x has number of 1 equal to 1? How many? 100. 100 choose 1, right? So that is that set, right? And then m is equal to 2, this set where there are 2 1s in the sequence of length 100, right? That's this. And m is equal to 3, 4, 5, and so on, all the way up to 100 ones, right? So m is equal to 100. Then there is only one single sequence where each element is 1, right? So that's what we are calculating using Excel, right? And then I can talk about occurrence of a single vector x. So probability of x, right? I can talk about the probability of vector x. That should be upper bounded by what? Lower bounded by what? So that is 2 to the power of minus nh, right? Minus epsilon, right? And then 2 to the power of minus nh plus epsilon. That one was what we have calculated over here, right? These two. So, let's just take a look at the order, right? Minus 6, minus 12. So that's what I have bold-faced here. And then if I sum them all up, these probabilities, right? Then basically that's the probability of m is equal to 2 to 8. So m is equal to 2 to 8, 7, 8. So probability of occurrence of these set, right? Even though this one is very largely drawn here, but since here is 100, this one is very tiny. Tiny set, right? Compared to the whole set. The size of the whole set is 2 to the power of 100, right? The size of this set is what? 2 to the power of nh, which in this particular case, nh is 28 something. So let's just say 29. So this versus that, okay? Okay? So that is that small, right? Right? But if you run the experiment, you will find the belongs to the typical set with the probability how much? 90%. That's what it is, okay? Or 95%, or 99%. You can make it happen, right? With the choice of epsilon and the block length n, right? So that's the convergence in probability. And that's the idea here. So that means, these are the outcome of typical. These are the typical outcome. Then I can emphasize these outcomes, right? And then represent. I can represent these guys, treat them equally likely, and then I assign 29 bits to describe each one of them, right? Why? Because that's the size of the typical set, 2 to the power of 29, right? So I need to allocate 29 bits to represent them, right? What about the rest of them? They almost never occur, right? So I can just use the equally likely representation, but the expected value of the representation system, because the probability is so small, right, it's going to be 0, right? And then this one, the bulk of the probability is covered right here, so it is going to be length 29. Okay. So that's what AEP, and this is the basis for the compression of digital information. Okay, when we use a computer file and compress it, right? What is the most famous algorithm that we use today? Zip file. Yeah, we will take a look at that one later on in this, probably next week. Okay, Lamper-Zip algorithm. Okay. So this compression, instead of 100 to 29 bit, can be actually, designed. Such a description system can be actually designed. Okay, right? That's what we are using today. Isn't it amazing? That's really amazing, I believe. All right, and so let me show you. I haven't downloaded Shannon's paper here, so but you should be able to find it in the internet. I didn't link it, so right here. That's the paper. If you read this, right, you can understand. You don't have to come to the class. At least for the first part, okay? I mean, first half of the part of the course. So here, he has proven the AEP right here. Theorem 3. Given epsilon and delta, we can find an n naught such that the sequence of any length n greater than n naught falls into two classes. So we can divide it into two. Typical set, non-typical set. That's what he's talking about. And what is this one? That is the entropy rate. The sample entropy, sorry. Sample entropy. What is H? The true entropy, right? Basically, that's it, all right? You can take a look. And then he talks about description of English language right here. So today, people talk about natural language processing. Shannon is the original person. Shannon has done that in 1948, right? So he uses the Markov process idea. So if you use, for example, in order to represent English in a Markov chain, right, you can think about alphabet of 26 letters. English, there are 26 letters, A, B, C, D, all the way up to Z, 26 letters. And the space, it says. And then first one, zero order approximation. So the zero order approximation is, so these 27 letters each occur with a certain probability, like we have done in our example, okay? Then this is the sample sequence, as you can see, right? Doesn't look like an English, right? How about now first order approximation? What do you mean by first order approximation? So when you define the sequence as a Markov chain, right? Each letter is a outcome of a random variable, right? So first letter x1, second letter x2, and so on and so on. And then there is an outcome out of these 27 letters, including the space, right? And then we can assign the probability, right? And then that's what he calls first order approximation, okay? Based on this probability distribution, this is the outcome, all right? So he says symbols independent. So he hasn't used the Markov chain idea as of yet. So because he said independent, the letters are independent, but there is a distribution on the letter. Okay, occurrence of each letter occurring in this sequence has a distribution. Right? Here is a uniform distribution. Here, not uniform. That's what I'm saying. Reflecting the distribution of a particular, let's say, article or paper or file, right? Then we can calculate the frequency of occurrence of each letter, right? That's what I'm saying, okay? And then he also talked about second order approximation, but this one is actually what he means by this one is Markov chain, okay? Markov chain based on a single letter, right? So for example, if you can talk about Markov chain of memory 1, so you can talk about, let's say, probability of x n given x n minus 1, x n minus 2, x n minus 3, and so on, is equal to probability of x n given x n minus 1. Then this is Markov chain with the first order, right? But if we say that this is equal to two letters, two previous letters, then it is Markov chain of order 2, and so on and so on. Order 3, and 4, and 5, right? If we increase the order, what happens? things are more complex, right? Instead of this one is taking 27 possibilities, right? 26 letters and a space, right? This one also has a possibility of 27. So set of 26, then Markov chain of order 2, you need the memory of 27 square, right? When you want to describe, find a table for Markov chain, you need this much rows, right? Hold on a sec. Sorry about this. 수업 시간이어서 전화 드리겠습니다. 예, 그러면 이거 좀 꺼놓고. 무슨 얘기인지 알겠어요? So, did you understand what I'm saying? Right? So, if we increase the order of the Markov chain representation, things will get more and more like an English, right? That's what you will see. So, this is the first order approximation. Aha. This one is better than these previous two. And the third order, this is actually a triagram, which is a second order Markov chain, which is looks better, right? And then we can also think about Markov chain based on words, right? So in this case, it is not a letter. Let's say there is a file or a news article, right? Written by Obama, President Obama, right? And then his vocabulary, his set of vocabulary is like 5,000 words, let's say, right? 5,000 words, right? And then basically each one is the Obama vocabulary set, right? Each one of them, right? We can do that. So this one we are representing the relation between words rather than each letters, right? So this will be more precise, right? If we want to compress an article written by Obama, we can use this dictionary to represent it, right? And then we can use some other person, let's say my daughter HJ, let's say HJ. Her English vocabulary is only 100, 100, right? Then we can learn this dictionary and then use this to represent an article written by HJ, right? Things like that. So that way we can compress more, right? So that's what this one is about, okay? So word representation, and then if you do second order word approximation, then this one look really like English sentences, right? Becoming like, right? So how do you define this Markov chain? How do you do that? So you need a table, right? Table. Markov chain, you can represent it with a table, right? So if we use a letter Markov chain all the way up to space, 27 of them. This is xn minus 1, right? And then here, you have 27 of them as well. A, B, C, D, E, all the way up to space, right? And then what do you need to do? If the previous letter was A, what is the probability of next letter being A? Probably is 0, right? We usually don't have AA appear together, right? And then how about B? Yeah, maybe it is likely. So we assign some probability. C, yeah, some probability. D and so on, right? You know what I'm saying, right? So we have a distribution, right? And then for B, we have another distribution, right? Another distribution and so on. So all we have to do is train your model so that you can learn this probability distribution for each state, right? And then if you now increase not only one letter but two letters, then this entry will be like AP, and so on and so on. How many of them? 27 square of them. And then for here, 27 square. This one is again one letter, so it is just stay as the 27, right? And then you can define the probability, right? So we can define this probability distribution. Then you have a model for a certain person, and this probability distribution depends upon a particular speaker, right, or writer, right? Then AI model can train this, and then you can predict the next letter, right? Most likely next letter, things like that. So that's the motivation for chapter 4, right? And he's talking about this Markov chain, right? Markov chain. Markov chain is what? One state, right? With a certain probability, you give jump to the next state, right? That's it. So you can draw that with the state diagram like that. All right. So you can take a look at that. And let's go back to our lecture note. Okay. So basically, chapter 3 was IID sequence of random variables. As you can see, chapter 4 talks about non-IID cases using Markov chain. Okay, that's the difference. So Shannon uses Markov chain to describe English. Okay, so zero order, first order, and so on. You have seen the example written by Shannon. And can we define a quantity which will measure, in some sense, how much information is produced by such a process, like an English writer, or better, at what rate information is produced? Okay. So in this case, obviously, these sequence of random variables are not IID. So, but if we use this type of Markov chain idea, then all we have to do now is define the entropy of Markov chain. That's it. Okay. And then per letter. So this one is based on a sequence, but since we can utilize some relation between these words and letters, then we can compress. That's the basic idea. Then basically all we have to do is utilize that probability into the measure that we would like to obtain, which is the entropy rate. Okay? So entropy rate is going to be defined as, let's say I have a sequence of length n, but this is not IID, and then I want to find out the entropy of this sequence, divide by the length of the sequence, which is n, right? Then it is going to be defined as a per symbol entropy. And then if we model it as a Markov chain, then all we have to do is entropy of a Markov chain. Okay? And then we will see the relation between the two. Okay? So that is the big picture. And let's take a look. This is the example that I have shown you a moment ago in Shannon's paper. And then some definitions for Markov chain. Basically, we say that Markov chain is a stationary process if the distribution is invariant over time. Okay, so here I consider n tuple vector, probability of that, and then this one is also n tuple vector, probability of that, but I have done the translation in the time. So instead of first incident, I'm doing this for t plus 1 incident, and so on and so on. If this one stays the same for all different t, then we say the Markov chain is a stationary process. And then Markov chain of the first order is just like this one, as we have done right here. And Markov chain is time invariant if the transition matrix P stays the same. Okay? So usually for a particular file or a particular speaker, this stationary distribution is fixed. That's why? Because it has a speaking pattern, right? Here, the person has a fixed vocabulary, and so on. So the initial distribution is S, then and then we can find a stationary distribution, which can be solved by this equation. S is equal to P times S, where P is a transition matrix. This one we have done in chapter 2, right? And if the initial distribution is S, right? So pi is equal to S, then the Markov chain is completely stationary, starting from the origin, right? So that's what that typical definition for Markov chain. And possible entropy is defined for a sequence of random variable. Note that I don't have that magic words IID, right? So this doesn't have that. There's no IID, right? So in general, this sequence of random variables are not IID, right? And then we want to find out the entropy of the sequence of n, where n is growing over time, okay? So n grows to infinity, sorry. Let's define the possible entropy to be this. So we write this way, following the book's notation, Carver and Thomas notation. We will write this as possible entropy.